recorded. Okay, recording's on. Hey, thanks everyone for joining. Welcome back to the TimeUp seminar. So today we have with us Srinivasan Arunachalam from IBM Research. So Srinivasan, he did his PhD from Centrum Viscun and Informatica and QSoft, following which he was a postdoc at MIT. Srinivasan's made several excellent contributions to quantum algorithms and quantum learning. And today he's going to share with us some exciting work on positive spectrahedra, invariance principles, and pseudorandom generators. So Srinivasan, whenever you're ready, over to you.
Thanks. Yeah, thanks for the intro, and thanks for inviting me to give this talk. Yeah, contrary to how he introduced me, as I've done a lot of work in quantum, this work is going to be completely non-quantum. Maybe I might use one quantum reference in the middle, but that's really about it. Like mostly this work is going, this talk is a purely classical result. Right, so I'll be talking about constructing pseudorandom generators for positive spectrahedron, and this was joint work with Penghui Yao, who's at Nanjing University. Right, if you have questions, if you just stop me in the middle, you can ask me at any time, and I'm totally fine with that. Right, so let me begin. What the starting thing is, what's a linear program? Like, right, so what's a linear program is just like, you're kind of like optimizing a linear function, and the space in which you're optimizing this linear function is called a polytope. So the geometric object that we care about to begin with is a polytope, and we want to optimize a linear function over a polytope. Right, and to be slightly more rigorous, what I mean by a linear program is it's defined by k vectors, w1 to wk, and then one cost vector in C. And in some sense, you're trying to find opt, which is you're trying to maximize this linear function C transpose x, subject to these k constraints, that the inner product between w1 and x is at most θ1, and the inner product between wk and x is at most θk. And all these inner products are just real inner products between two n-dimensional vectors. Right, and you want to find the maximum of C transpose x subject to these k constraints. And that's what a general linear program is. And what's nice about a linear program is it's efficiently solvable. So efficient in k, n, and so on. And that's why it's so interesting, and it has so many applications. Right, so let's try to get a little bit more intuition like as to, and the thing I care most about is what is the space over which you're optimizing here, which is what I call a polytope. So let me try to give a little bit more intuition as to what a polytope even looks like. Right, so first let's start with the half space. So half space is just like a constraint that just splits Rn, in this case R3, into like two sides. For example, like this orange thing is just splitting this R3 into like top and left, for example. So in a way, you can view a half space as just a constraint in Rn that just divides the space into like say plus and minus and so on and so forth. So to be slightly more rigorous, so let's just say H1 is my half space that takes as input in Rn, and it's just going to tell me what it's just going to output a number 0 or 1, depending on whether you're to the left or right of the half space. And to be even more rigorous, what I mean is the half space is defined by a vector W, and we say the half space evaluates to 1 if and only if the inner product between W and X is at most a number called theta. So that is what is a half space. Right, and next. Right, and another way to write this condition is just like the indicator function of whether w dot x is at most theta, where when I mean by square brackets, I just mean it's the indicator function that evaluates to 1 if the predicate is true and 0 otherwise. Right, and what's a polytope? A polytope is just an intersection of half spaces. So in some sense, you could just like say, like for example, like this, the top thing just divided the space into left and top and bottom, and then this thing puts an extra constraint. I would like it to not only divide top and bottom, but I would like to put in more constraints, and end of the day, I would like to only optimize over the space inside all these, where all these k constraints have been satisfied. So half space is just one thing, and when I put in k half spaces and want everything to be satisfied, that's what is a polytope. Right, so to be slightly more rigorous again, so let wi be a vector in Rn and theta I just be a number in R. A k-facet polytope is just an indicator function of k different half spaces being satisfied. So this and is just a logical and. So h1 of x should be satisfied, that is w1 dot x should be at most θ1, h2 of x should be satisfied, that is w2 dot x should be at most θ2, and so on and so forth. So there are k different half spaces given by h1 to hk, and I would like the x's for which all these k different half spaces are satisfied, or all these k different The x's should satisfy wi dot x should be theta I for all these wi's, and that is what is a polytope. Again, so polytope just looks at the x's which satisfy all these different half space constraints put together. That's really an intersection of half spaces, and that's a polytope. Right, and then it's now not hard to see that this opt is nothing but C transpose X when X lies inside a polytope. That's really it. Because we want these K constraints to be satisfied, and this K constraints being satisfied is exactly a polytope. So linear program is just maximizing linear program just maximizes a linear function over a polytope. That's it. And again, like linear programs have found like many applications, for example, in optimization, combinatorics, geometry, computational complexity, and so on and so forth. So they found several applications. I'm not going to talk about them now. But the more generalized object that I'm going to be talking about in this talk is a semi-definite program. And in some sense, what is the space over which you're optimizing a semi-definite program? So firstly, what's an SDP? So in SDP, you're still optimizing a linear function, but you're going to enlarge the space. So in some sense, you're not just optimizing over a polytope, which was clean, like a bunch of K facets, and you're just putting them together. You're optimizing a linear function over a more funky object called a spectrahedron. And to be slightly more rigorous, so what is an SDP? It has the following form. Earlier, W1 to WK were just like half spaces, they were just constraints. But here, W1 to WK are symmetric matrices, n by n symmetric matrices. And at the end, you're going to again maximize C transpose X, a linear function, but subject to a slightly more generalized constraint. X1, W1, so Xi's are all numbers in R. Xi is in R, W1 is a symmetric matrix. And what I mean by this loner ordering is when I say this is at most this, or when I say two matrices C is at most D, I mean D minus C is positive semi-definite, or all the eigenvalues are greater than 0. So again, a semi-definite program is you're still maximizing a linear function, C transpose X, but subject to a constraint, a matrix constraint. So X1, W1, all the way to Xn, Wn is at most B. And it's not too hard to see that if I let all these Wi's just be diagonal matrices, then I get back the exact question, then I get back just the linear program. So in some sense, a semi-definite program is a generalization of linear program when these symmetric matrices are not diagonal. So allowing off diagonal term allows you to optimize over a larger object. And I'll tell you why it's interesting in a minute. But one annoying thing is like the semi-definite programs look extremely general. Like, I mean, for example, like the two most, like a cylinder is a semi-definite program, and then this elliptope is a semi-definite program. And eventually I'm going to be talking of even more funkier looking spectrahedron. So they don't have the nice, beautiful structure that a polytope has. So easily I can write a polytope as just K half spaces, just put them together, that's a polytope. But a semi-definite program is kind of, it could look a lot more weird and it would look a lot more technical. Right. And again, so sorry, yeah.
Can still be represented as like an end of like indicators?
So technically speaking, a semi-definite program is like an intersection of infinite constraint half spaces, but you could approximate a semi-definite program by another polytope with exponentially many constraints.
Okay, thanks.
To exactly represent it, you require infinite constraints, but you can approximate it up to some approximation things which I won't get into by exponentially many constraints. Thanks. Right. So as I said, if I let these W1 to WK be diagonal matrices, you get back linear programs, but semi-definite programs allow even off diagonal terms or even non-diagonal matrices. But the nice thing is semi-definite programs are still efficiently solvable in N and K. So you can even, not only is a linear program solvable in polynomial time, even a generalization of a linear program, that's a semi-definite program, can still be solvable in polynomial time. But unfortunately, these objects are not very well understood. And I will again come back to this in a couple of slides. Like linear programs are extremely well understood. SDPs are not super well understood, but we still have many applications of this. Like for example, like the Gomez-Williamson algorithm to approximate max cut is the semi-definite program. Then there's SOS hierarchy, and even like seminal results in quantum computing. Like for example, QIP equal to P space, QIP equal to P space was proven using understanding semi-definite programs for interactive proofs. So we still have found many applications of SDPs, which have been like the reason why people are do care about it a lot. Right. The first two slides have been about the first part of my talk about semi-definite geometric objects. The next slide is going to be about pseudorandom generators. And the slide after this, I'll put both of these together. Right. So what our PRG is just a function, and it's a function that expands randomness. So the typical photo that you might see in many talks about a PRG is it takes like our pristine bits or our golden coins, and it expands it to n silver coins. These n silver coins are not going to be purely random; they're going to be pseudo-random. But these R bits are like purely random. So in some sense, you can expand pure randomness to kind of like pseudo-random bits. And to be slightly more clear again, so we say let's consider a class of functions, script C, which is just a class of functions f that map n bits to 1 bit. We say a pseudo-random generator is a function g that maps r bits to n bits, again r here to n bits, and we say this function fools the entire function class if for every function in the function class, no function can distinguish whether I gave it pseudo-random bits or uniformly random bits. So again, so maybe forget this first predicate for every f. Just look at, fix a function f. The function f cannot distinguish whether it got pristine uniformly random bits, that is pristine bits on n bits, or it got like fake silver coins. So like, what I mean by fake silver coins, that means I fed in pure silver coins, golden coins r, I got in fake uniformly random bits, which are called pseudo-random, and the function f cannot distinguish whether I got pure uniform randomness or fake uniform randomness. And this function g fools this class if this holds for every function in the function class. And of course, there is one trivial way to construct a pseudo-random generator, just pick r equals to n. So if I take in uniformly and let it be the identity function. So like then, for example, like g of x is just again uniformly random, u is also uniformly random, and this left-hand side is 0. But in the entire in the field of pseudo-random generators, you would like to optimize something called R, which is called the seed length. And typically you would like the seed length to be polylog in all the relevant parameters. And this trivial thing that I just told you is when R is equal to n. So that's not nice. We would like pseudo-random generators for which R is equal to polylog in n. But right, so the whole point in this field is to understand, construct pseudo-random generators or PRGs for which the seed length or R is polylog in n, and maybe some other parameters that define your concept class. And in this field, like one of the holy grails is to kind of like construct a PRG against all possible class of polynomial size circuits. So let script C just be the class of all functions that can be computed by polynomial size circuits. And can we construct a PRG for script C unconditionally? And if we could do that, that would have this breakthrough consequence of BPP equal to P, that is a class of all bounded polynomial time probabilistic algorithms can be de-randomized. But yeah, I think we're very far from this. I don't even know what's the state of the art, but this is one of the holy grails in this field. But the thing that I'm going to be interested about is constructing PRGs for geometric objects. And what I mean by that is, let's just say script C is the class of all functions that can be, say, represented by a polytope, or can be represented by a spectrahedron. We know that linear programs can be solved in polynomial time. So if we had a randomized algorithm for, say, counting the size of polytopes and so on, can we de-randomize it? And constructing PRGs for geometric objects has been like a rich area of study. Like there have been many, many works that are, for example, just looked at specific half spaces, polytopes, looking at constructing PRGs for just geometric objects and seeing what is the seed length dependence for these functions. So I'll quickly overview these PRG works in the next slide. But if you have any questions, again, you can stop me at any time. Right. So let's see. So this, right. So in 2009, there was this really amazing work of Meka, Zuckerman, and Diakonikolas et al., where they constructed PRGs just for half spaces. So they first construct just a half space, a single half space that divides Rn, and they say, can we fool a half space? And I'll talk a lot about this Meka Zuckerman framework in a few slides, but they had this beautiful framework which Meka Zuckerman introduced, and based on this framework, you can construct PRGs for free in some sense if they satisfy certain things. And finally, I think after a few works, Gopalan, Kane, and Meka, I think they have optimal PRGs for half spaces. And when I mean optimal, it's polylog in all the relevant parameters. And then there was, of course, a generalization of half spaces, which is a polytope. So if we can fool one half space, why not fool an intersection of half spaces? And this was started by Harsha, Clivens, and Meka in 2013. And And the point is they could fool polytopes which satisfy certain constraints. We'll again talk of Harshad-Leiben's Meka in a few slides. But eventually, only like a few years back, like in STOC 2019, did Ryan O'Donnell, Rocco Servedio, and Liang Tan, they finally had PRGs for polytopes with seed length that is polylog in the relevant parameters again. And finally, I mean, there's another line of work which I haven't spoken about. So like you can view a half space as just a linear function. So as I said, like it's inner product between W and X. So that's just a linear function in X. But how about looking at a slightly more higher degree polynomial of X? So think of P as a higher degree polynomial in X1 to Xn. And let's just say I look at the sign of such a polynomial. And that's a polynomial threshold function. And again, the work of Meka Zuckerman gave a way to construct PRGs for PTFs or polynomial threshold functions. And I think, as far as I know, like these, the seed length that they have is still optimal for the Boolean space. But there have been lots of subsequent works that have kind of looked at the Gaussian space, trying to fool it in the Gaussian space. And I think I think state of the art for the Gaussian space was done only last year by O'Donnell, Servedio, and Tan. And kind of the motivating question for this work is a spectrahedron can actually be viewed as a generalization of half space, a polytope, and a PTF in one framework. So like a half space is clear, like a half space and polytope is clear because kind of like, as I said, like diagonal spectrahedron is just a linear, it's just a polytope. So at least half space and polytope should be clear why spectrahedron generalizes it. And to see why it generalizes PTFs, I don't think I have time to talk about it, but one indirect way to view this is a spectrahedron is just asking whether two matrices are kind of like, when I say like A minus B is positive semi-definite, by using Sylvester condition, you can write this as the intersection of the determinants of polynomials. And so you can view a spectrahedron as kind of an intersection of polynomial threshold functions. And there's a one-to-one, like it's an if and only if in some sense. So in fact, spectrahedron can also be viewed as maybe a necessary and a sufficient condition to also fool polynomial threshold functions in the end. So a natural question is, can we construct PRGs for spectrahedron?
Shay?
Yeah.
So when we're considering PRGs for circuits and computational devices, then this is often being done in the context of de-randomization, as you mentioned, because we want to fool, certain computationally bounded device. When we're designing PRGs for geometric objects, is there any inherent connection to the randomization and things like that?
Right. So one of the important connections, for example, like let's just say I give you an integer linear program and I ask you how many satisfying assignments are there in this program. And the question is, and there are randomized algorithms for counting the number of satisfying solutions to an integer linear program. And the whole point is you would like to de-randomize these algorithms that count these solutions for these programs. So I think that was one of the first motivations for Harshad-Leiben's Meka actually, to de-randomize these algorithms for these counting algorithms. And that's why they came up with PRGs for polytopes. Admittedly, it's kind of artificial to construct PRGs for spectrahedron because like you don't really care about counting the number of satisfying solutions to a semi-definite program, but I just think it's interesting nevertheless to fool this class of objects.
Yeah, thanks.
Good, so let me state our main results. Right, so again, a spectrahedron is just, okay, I'm going to be looking at a Boolean spectrahedron. And by that, I mean, again, with the kind of counting motivation in mind as the set of all x's that satisfy this constraint. So x1, a1 to xn, an, they are at most b. I mean at most b, it's at most b in the lower ordering. And I'm going to be, we don't fool the class of all spectrahedra. We are going to fool only a class of spectrahedra because of the limitations of our techniques. But the assumptions that we're going to be making is first, I'm going to assume that A1 to AN and B are positive semi-definite. So in general semi-definite programming, AI and B could be arbitrary symmetric matrices. But for now, I'm going to be assuming, for the rest of this talk, I'm going to be assuming we are positive semi-definite. Second, I'm going to be assuming that this is not an assumption, but this is just our PRG is going to depend on this parameter, the width of this program. And when I mean width of this program, I mean summation I, AI squared should be at most M times identity. So the largest eigenvalue of all the summation AI squared should be bounded between 1 and M. And finally, I need something called regularity. So I'm just going to assume that all these AIs, none of them are going to be like dominating the rest of them. So in some sense, I don't want like A1 to AN minus 1 to be tiny and AN to be super large. in terms of eigenspectrum. So I would like all of them to be kind of nice and bounded in some sense. And this regularity will come back again in a couple of slides. I'll tell you why we hit upon this condition in the first place. And the main theorem is the following. So we look at the class of all spectrahedron, or the class of all functions, each function defined by a AI and B. And we can fool the class of all these functions by a PRG G with seed length that's log in n, log in k, and depends on m comma 1 over delta. So the point is it's optimal, well, close to optimal in terms of n and k dependency because you would like it to be poly log in n comma k. But of course, it's not optimal in terms of the width of the program and also delta, 1 over delta. Maybe you could make it log 1 over delta, and we don't know how to do that. So to state it slightly more clearly, so what this PRG states is this function g, it cannot differentiate between when I gave it uniformly random bits. Sorry, think of the object s, think of it as a function f, s as a function as the indicator function. Now, you cannot distinguish whether I gave f uniformly random bits or pseudo-random bits. And that's what a PRG by definition is. And the nice thing is, sorry.
In the definition, like x should range over -1 to the k, right?
No. The AIs are k by k matrices, but they're n such matrices.
Oh, I see. Oh, no, I see. Thanks.
X1, A1, X2, A2, all the way to Xn, An, but the AIs are k by k matrices.
Okay, so this is like, so k is just like, okay, it's the size of the matrices, and n is the number of different constraints that you have. Okay, thank you.
Exactly. So think of it like a polytope in Rn, but with k facets.
Yeah, good.
Great. Good. And the main technical contribution of this talk is we're going to construct an invariance principle for positive regular spectrahedra. Positive because these matrices are PSD, that's the assumption, and regular because we have this regularity condition. And for the rest of this talk, I'm just going to be talking about how to construct an invariance principle. Technically, I'm not going to prove main theorem, but I will tell you how this framework of Meka Zuckerman says that if you construct an invariance principle, you immediately get a PRG for free in some sense. So I'm going to be talking about the technical work in constructing an invariance principle. And then you could maybe refer to our paper. It's just like a one-page argument where you go from invariance principles to a pseudo-random generator. Right, so I'm going to, for the rest of the talk, first, I'm going to talk about this Meka Zuckerman framework. And then I'm going to talk about how Harsha-Kleiman's Meka used the Meka Zuckerman framework for fooling polytopes, and then how we improve upon Harsha-Kleiman's Meka to generalize things to the spectrahedron case. And again, if you have any questions, again, maybe now's a good time to stop me and ask.
Yes, Srini, so I have a question about the intersection of PTFs. Can you get implications for this class using a PRG? Because you mentioned a connection, right? Thanks.
Right, so we do have right, good. So the point is, this connection would have been nice if, for example, like we do have a PRG for intersection of PTFs, but this intersection of PTFs is highly structured because we are imposing this positivity constraint. So we can't fool like arbitrary PTFs. We can fool like a structured class of intersection of PTFs with seed length, in fact, depending on K. And the best known seed length right now, even for arbitrary PTFs, is 2 to the K.
I see, thanks. So K becomes the degree, is that the intuition?
Exactly.
Okay.
Exactly. Right, so we do elaborate on this connection again in the paper. It's just like a half-page argument, like it's a trivial connection. Yeah.
Sorry, here G is somehow efficiently computable, or we just prove it's
no, it's efficiently computable. That's right. It is efficiently computable.
Okay.
It's explicit and everything. Yeah.
Thanks.
So I have a question. So inside the log in the R expression is only K or also M and 1 over delta?
Sorry. Okay, it's log K. Oh, sorry. M and 1 over delta are not inside the log. I'm sorry. So it's log K. So M times 1 over delta times log K. Think of it that way.
Okay.
Sorry. I should have put a bracket around this log K to shield it from the rest. Good. So let me first tell you this Meka Zuckerman framework. I just think it's really beautiful, like how they construct PRGs from invariance principles. So the gist is the following. The punchline is, if you give me invariance principles, you can kind of construct PRGs with some additional assumptions and things. But the hard work is generally in proving invariance principles. So what's an invariance principle? It's a generalization of the Beryacine theorem. Now, what's the Variation Theorem? It's kind of a generalization of the central limit theorem. So what's the central limit theorem stating? It states the following. So if we take a bunch of random variables x1 to xn with mean 0 and variance 1, it says that eventually, if you just look at the sum over x1 to xn, we normalize it by square root of n, you eventually converge to the Gaussian of mean 0 variance 1. But what the central limit theorem doesn't tell you is how fast this convergence happens. For example, if I want the difference to be at most epsilon, how large should I let n be? And that's where the Beryacine theorem comes in. And the Beryacine theorem says is for every u, that's a real number, it tells you how fast the left-hand side converges to u and how fast the right-hand side converges to u. And it gives a quantitative bound on the difference of these two quantities. There should be an absolute value here, sorry. So it tells you when is the left-hand side at most, how large should I let n be so that the left-hand side is at most u and the right-hand side is at most u. And again, the C is a property that's going to be important, but not for this slide. I'll come back to it later. And this is what the Beryacine theorem tells you. And right, so this was proven by something called the Lindeberg method. This is not 2022, this is 1922. So like literally a century back, they proved the Beryacine theorem, and that has been, again, crucially used in all the works, and even in our work, we're going to generalize the Lindeberg method. And I will tell you what this method is in, again, a couple of slides. Right, and in some sense, the intuition is the following, like understanding Boolean space is generally hard, but what the Beryacine theorem allows you to do is kind of like move from the Boolean space to the Gaussian space and try to prove a result in the Gaussian space where generally life is more easier to prove any result. Like it might be equally hard, but at least it's simpler than the Boolean setting. And this translation between the Boolean and Gaussian setting is allowed to, you could do it by the invariance principle. So again, let me tell you how Meka Zuckerman was used so far. Like again, the punchline is if you can prove a version of invariance principles, you get pseudorandom generators. That's really the punchline. And how they used it so far is the following. So let's just go back to Meka Zuckerman back in 2009. They have the half space version. Again, recall that this is the half space is a set of all plus minus 1 to the n strings, such that wi xi is at most theta, one constraint. And what they observed is if the w's are smooth, and what I mean by smooth is like all these w's are kind of like equally balanced. Say the L4 norm is at most the L2 norm, or none of these wi's are very dominant. And in that case, they show that wi xi actually converges to the Gaussian. And with that, they kind of almost got an PRG for free. But well, I won't say free, you have to do a little bit more work, but really the point is like they observed that wi xi converges to the Gaussian, and that was good enough.
Okay, can you repeat what is smooth in this setting?
Okay, one way to view smooth is the following. Just think of the vector w1 to wn. I do not want like w1 to be 1 and w2 to wn minus 1 to be 0. So I don't want like one completely dominant coordinate and the rest of the coordinates I want to be tiny. I want all of them to be kind of like equally, say at most say 1 over, say everything is at most say 1 over 100 or something like that. Nothing should be large. Everything should be kind of equally close to one another. Okay. And to quantitatively put it, I think the condition that they had is the 4 norm of W should be at most some number tau, for example. That's their regularity condition. And that's why we also need to impose the regularity condition. Okay.
And the 4 norm comes just because like you bound some Taylor series or something like that?
Yeah. The Taylor series, everything is going to come again in the next couple of slides. Yes. Right. So this was Meka Zuckerman, and how Harsha Clemens Meka generalized this was the following. Again, recall this is a polytope. It's a set of all plus 1 comma minus 1 strings, such that k different constraints are satisfied. And what they observe is if all the W1 to WK are smooth, are regular in the way I just said, then if you look at this inner product, that is inner product. So again, there are k rows and n columns. So k facets acting in Rn. If you take the inner product between W and X, so W1X, W2X, all the way to WKX, it eventually converges to Gaussian in G1 to GK. And what's most important is what's the rate of convergence here? That's most important in all this works. And I will come back to the rate of convergence in the next slide. But The crucial thing is they show that eventually it converges with a nice rate of convergence. And like a subsequent set of works, what they do is like finally in OST in 2019, they show that this convergence happens with a nice rate without requiring this. Sorry, I overuse the word smooth and regularity, but in the entire slide, when I mean regularity, I mean all these WIs are kind of uniformly balanced. None of them is like hugely dominant compared to the other. But OST can fool polytopes even without this assumption. But yeah, that was like I think like a few works between 2013 to 2019, slowly removing this condition. And finally in 2019, they removed this altogether. Good. So, right. So the hard work, as I said, is in establishing this inequality here. This is the invariance principle with nice error dependence. And I will tell you how they established this. Again, recall this is a polytope. And one way to write a polytope is you can just write a matrix capital W, which is just this matrix, capital W, K by N matrix. And you would like the K by N matrix to be at most a vector. And again, they establish an invariance principle for polytopes. And what I mean is, okay, when I mean regular, I mean, just say, for example, the 4 norm is at most tau for the time being, for every single WI. Right. And the crucial thing that they observed is, if you look at the polytope Wx at most theta and Wg at most theta, that is instead of x, I replace it by a Gaussian, then the expected value of this polytope and the expected value of this polytope is at most tau poly log k. So recall a trivial bound would be tau times k, but they got the error dependence to be tau times poly log k. So that's really where the nice work comes in. And the way they prove equation 1 is actually in a 3-step process. And the first thing is they establish a smooth invariance principle. And what I mean by smooth invariance principle is the following. So first thing, they observe that this indicator function is highly like discontinuous. Like I don't even know how to prove such a statement when I have such a discontinuous object. So they said, let's replace this indicator function by a nicer function. So Wx is a k-bit thing because W is a k by n matrix and x is an n-bit string. So Wx is a k-bit string. It's not bit, it's a number in Rk. So they say, let's first consider a smooth function in Rk to R. And then they say, let's bound the following quantity. So instead of looking at this indicator function, let's just apply a smooth function. Maybe I'm overloading the word smooth here, but I'll tell you what I mean by smooth in just a couple of in a minute. Let's just consider applying a smooth function to W times X. So I don't care about the indicator, I just care about W times X and applying the function O times to W times X and O to W times G. Then what they do is they actually write the Taylor series expansion because O is a smooth function, I can write it. And they bound the terms in the Taylor series expansion by tau times log k times the third norm derivatives of O, third order derivatives of O. And the way they prove this is by the Lindeberg method again. So they write the Taylor series expansion of O, and then they observe that the uniform distribution and Gaussian distribution have matching first and second moments. So you get the third moments remaining. And that's why they get the third order derivatives of O. Great. Now, and again, because O was smooth, and what I mean by smooth here is, I mean, like all the derivatives of O are pretty nice. Let's just say, for example, like all these derivatives of O are just say, in a wishful world, everything scales with poly log n k. And so that's what I mean by a smooth assumption. So let's just say if all the derivatives are small, then kind of we have established a version of one. We have not established one yet. First, there are 2 differences. One, we still haven't bounded this. We just said like if it O was smooth and if these norms are small, then we are in good shape. But the second still thing is we have gone from an indicator function to an arbitrary smooth function. There need not be any relation between this quantity and this quantity. But they first established item number 1, which is I think interesting in its own right.
Srini?
Yeah.
So far, this seems like very similar to the strategy of like the invariance principle for the hypercube. Are there like significant changes here?
I just think the crucial thing that's happening here is ensuring this log k dependence. That's really where most of the work comes in.
I see. Okay.
Apart from that, I think these techniques are pretty well known now. Like it's almost been like 9 to 10 years since their work, but I think it's pretty standard now. It's just that getting the right dependence is where the hard work comes in. Like trivially, you get a k dependence and they get log k times this dependence. Recall we want to establish equation 2, and so far we have established equation 3. And again, we would like to go from equation 3 to equation 2, and there are two things that are remaining to be bounded. Why does O have anything to do with this indicator function? And why should, if supposing we could show O is close to this indicator, why should the 3 norm be bounded even? And that's where it comes in, this beautiful idea of Benkes modifier. So it so happens that, again, we care about this indicator function. We don't care about this O function. So it so happens that there is this function established by Benkes, a mathematician, like, I don't know what was his motivation back in 90 to establish that you can approximate the orthogonal function. And I mean by orthogonal function, I just mean this indicator function by actually a function O with very nice properties. So in some sense, what he says is the following. We can come up with a function B, the modifier, the Benkes modifier, which approximates max over I zi. So in some sense, this is like an AND function. So he says we can approximate the AND function, which is discrete, by a continuous function B. Sure, you could always do it, maybe like just like kind of like always closely approximate it. But not only that, he got all the derivatives to be scaling with poly-log in K. So it so happens that so now very nice. So like we got the right O. In order to approximate the orthogonal function, I'm just going to let O be the Benkes modifier. And amazingly, equation 3, we can upperbound everything on the right-hand side by poly-log in K. But there's still one thing remaining. Like kind of, we know that B only approximates this function. We don't know B whether, so we know that O applied to WX is close to this indicator function, but it's not exactly equal to it. And that's what I mean by this approximate, squiggly approximate here. When Z's are nice, this is a good approximation, but when C's are very close to the orthogonal function, let's say very close to 0 and so on, it's a very bad approximation. So we only know B approximately agrees with O, not exactly. And this is where the problem is. So the point is only across the boundary of so if you look at a polytope, only the boundary of a polytope, B and O are disagreeing, where B is a smooth approximation and O is the actual approximation you care about. And so what they said is, okay, fine, this is a problem. Like we can establish a version of 2 in terms of 3, but 3 is not very close to 2. Like we can only close it when we are very much in the interior of a polytope, but when you're in the boundary of a polytope, we are still struggling. We don't know what to do. Then they just made this observation. What if supposing the mass of a polytope sitting in the corner is small in the first place? Maybe we're fine after all. Like end of the day, we just need to prove these two expectations are close. But maybe the expectation contributions around the boundary are very small in the first place, or maybe it's okay after all. And this is true after all. What they can show is two things. One, in fact, is the boundary, the Gaussian mass sitting in the boundary of a polytope is small. And not only that, that is sufficient to establish equation 2. And the hard part is again proving that the surface area of a polytope is small, or that is the Gaussian mass sitting in the boundary of a polytope is small, and that is precisely captured by something called a GSA, or the Gaussian surface area. And again, beautifully, there's this very nice result of Nazarov, proven in 2003, where he shows that the GSA of a polytope is actually square root log K. So again, it was lucky that everything in this slide, for example, like it was nice that I would say lucky, but it so happened that the Benkes modifier has poly-log dependence in the norm. The GSA again has square root log K dependence. So in some sense, establishing equation 3 was sufficient. Equation 3 was sufficient because like to go from, you could plug in O to be the Benkes modifier. So now equation 3, everything is at most poly-log in K. And again, to go from equation 3 to 2, you just need to show that 3 is sufficient because the mass in the boundary is small. And again, that is small because of GSA. So everything from 3 to 2, it's done. And again, just based on this, you can construct a PRG for free based on the Meka Zuckerman framework. The hard part is in establishing equation 2. Good. And yeah, being a quantum person, what we thought about when we looked at this, like Pengui and I, we thought about just what's a half space is just like Wi, Xi at most theta. Let's just replace everything by matrices. That's what we mean by quantize everything. And spectrahedron is just like a naturally quantum friendly object when you replace all these Wi's with just matrices. And there are two immediately stumbling blocks. And the first thing is the spectrahedron naturally deals with eigenvalues of matrices. So when I mean by A less than B, sorry, or this summation less than B, I mean that the eigenvalues of B minus this are at most 0, at least 0. And as far as we know, we don't even know a Lindeberg type argument or a hybrid method argument for spectral modifiers. Like we don't even have it when we have to deal with eigenvalues of matrices. We have it only when we deal with like a Beryacine kind of thing works only when we have numbers. But it doesn't work when we have like, we're working with spectrum of matrices. And right, we don't have such a Lindeberg type argument, and that's our first contribution. Right, we first established an invariance principle only for the Benkos modifier, but when dealing with eigenvalues of matrices. I'll talk about this in more detail for like 10 minutes after this. And the second thing is, even if we establish an invariance principle in the previous slide, I showed that first things first is like, there were 3 items in the previous slide. One is for a smooth function, you need to establish invariance principle. 2, you need to be lucky that the Benkos modifier works. And 3, you need to establish anti-concentration. So here, item 1 captures the first 2 things. For the Benkos modifier, we can establish an invariance principle. We still need to establish an anti-concentration. And that's our second contribution. Like, it so happens that polytopes are nice. The very geometric structure, for example, a polytope here, like you can understand what the GSA of the boundary is. But for a spectrahedron, it could be like arbitrary object. Like it could look extremely weird because it contains even like intersections of polynomials and so on. So we do not know how to go from like modifier closeness to CDF closeness. And that's where we establish something called the Littlewood-Offer theorem for matrices. So we show that you can establish anti-concentration for matrices even. And that's a matrix version of Littlewood-Offer theorem. Right, so I think I have like 15 minutes maybe, and I will quickly, like, yeah, maybe like in 10 minutes, I will try to sketch like what's happening in item 1 and 2, but I can't do complete justice, of course. Right, and before I talk about this invariance principle, I just need like 2 quick definitions. So one thing is, what's a spectral function? So a spectral function is just a function that takes a matrix as an input and outputs a real number. So like, for example, like, but not only that, it just acts on the eigenvalues of matrices. So like, think of a spectral function f being a function g that acts on Rn to R, but g only acts on the eigenvalues of matrices. And for example, simple examples include determinant, traces, matrix norms, and so on. So these are all spectral functions. They take a matrix, and the value of the determinant, trace, and matrix norm depends only on the eigenvalues of this matrix. And the next thing I need is the derivatives of matrix value functions. So again, in like when I sketched Harsha-Kleiman's Meka, I needed the Taylor series approximation, but we are no longer working with real numbers. We are working with matrices now. So we need derivatives of matrix value functions. Right. So the first thing, what's a Taylor series approximation? It just says like, if you have a function from R to R, we can find the Taylor series approximation of H around the number A as just this expression. And when I say H prime of A, it's the derivative of H at the point A, and it just takes the limit of H of A plus F that I just move H by an epsilon part, and then I divide it by epsilon, and I look at this limit. So this is a standard Taylor series. And one can generalize Taylor series to something called Fréchet series. So when you don't have just R to R, but matrix to matrix. And these are derivatives that people look often in the math community in Banach spaces. And as I said, it's like derivatives in the Banach spaces are pretty similar to standard calculus, but they're slightly more complicated. For example, like the Fréchet derivative of the function, the function A on function F on A with respect to direction B is precisely this. It's kind of similar to standard derivative in that you, for example, that 1 over S is similar, and you're kind of like moving A by S times B and then subtracting A and then looking at the function. So it's kind of similar, but as like already this expression looks slightly complicated, and that's actually not just like an artifact of just viewing it. It's just that these derivatives are actually very hard to compute. And even like basic properties are very poorly understood. For example, like things like continuity, Lipschitz continuity, differentiability, and so on in standard calculus have been known for centuries, but these things for Fréchet series and matrices, they have only been proven in the last 2 decades. Maybe even a result that I used was proven in the last decade. So these things are very poorly understood, and people are still continuously trying to understand like what are the matrices for which Fréchet derivatives are well, you can understand them, and so on and so forth. Good. So let's see, now with this, let me try to tell you how we establish our invariance principle. And recall, this is the goal. I would like to show the following. I would like to replace summation xi ai minus b. So recall a spectrahedron was xi ai at most b. So I'm just taking b to the other side, so it's xi ai minus b. And now I'd like to replace x by g, first things first. And not only that, I would like to show for the Benkos modifier acting only on the eigenvalues of these matrices, these 2 quantities are close. And again, what's most important is the convergence parameter. What we show is it's at most tau times poly log n k. Very similar to Harshad-Kleiman's Meka, but now we are acting on the eigenvalues of matrices when we replace Boolean by Gaussian. Right, and again, we go using the standard route, the hybrid method. So the first thing we do is we kind of like hash the sum. So this is a sum over n things. It's k by k matrices, but we hash the sum.
Sorry for the interruption. What does it mean in the absolute value in the first line? So it's probability of sum of two functions, right?
Actually, the point is, I think there should be an expectation. Sorry, it should be an expectation, not the absolute value.
Okay, cool.
Sorry. I'm sorry.
It's okay.
Yeah, okay, sorry. Right. So first thing we do is we kind of hash the sum over n things, and we hash it in a way that's kind of pretty. And the way, what's nice is the following. Let's just say, for example, like we look at the first block of this hash, and we can write it as the following. We hash it in a way such that you can write it as summation xi ai minus b. You can write it as a sum of two terms. The first term is qx. It just depends on x, and the second term depends on x comma g. And the same thing, you can do it for this sum as well. So an expectation, the left-hand side of here is the same as the expectation on equation 4. Right, and so what you need to observe is just the fact that the second term is the same in both, and the first term depends on Boolean here and Gaussian here. That's the only difference. Next, what we do is we kind of follow the well-trodden path of we just write the Taylor series expansion, which in our case is going to be Fréchet series expansion.
So what is P in this decomposition?
I'm not explicit about it. Like it's a complicated expression. You can think of it this way. You can hash the sum in a way such that you can write this expression as some matrix that depends only on x. And
you factor out like the Gaussian part and the
exactly. I would like to separate these two things in a nice way.
Okay, I see.
And the reason I separate this will become clear in just a minute. So right, so we have equation 4 now. What we do is we write the Fréchet series expression for this, for both these terms. So if you write the Fréchet, so I just denote b circ lambda as b subscript lambda here, and we write it as qx plus g. We can write the Fréchet series. We can write it like this is the 0th order, first order, second order, and third order. And we can again do it for qg. Again, recall everything is the same except like these two matrices are the same. What's the difference is qx and qg here. Right. And again, we observe like what it's not too hard to observe that the same color terms are equal in expectation. So if you take an expectation over x and g, because the Boolean and Gaussian have like matching first and second moments, you can show that the red in expectation is closed, the brown in expectation is closed, and the blue in expectation is closed. So in order to bound equation 4, after writing the Taylor series out, it just amounts to bound the third order derivatives. Here, the third order derivative is qx, 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 and here is qg, qg, qg. So, right. So, I mean, I'm kind of hiding many things under the rug here, but I don't want to make it complicated. But the idea is we want to replace x by g in the first equation on the top. The way I do it is by first hashing and writing it nicely. We then write the Fréchet series. We observe that the moments are the same, first and second. So we are left with the third moments to bound right now. And as I said, like Fréchet series are very hard to bound. Like we have zero idea of how to even bound this, but we got lucky. There's a mathematician Sendoff. What he did is he kind of gave kind of expressions of how to bound. He gave a tensor way to represent Fréchet series for spectral functions. Recall we're working only with spectral functions here. So that's good. So at least we have a way to understand what these expressions here are. Maybe we don't know it explicitly, but we can kind of have a way. So we need to bound the third order derivatives. And the hope is to use a Sendoff's result saying how to understand these third order derivatives. But if you write out his expression, what you get out is like a bunch of like 7 terms, and each one increasingly more complicated. The first 3 terms are all diagonal terms. And the point is, this is what Harshad-Kleiman's Meka and all the subsequent works had to bound, only 1, 2, and 3, because a polytope is just a diagonal spectrahedron. But for us, it so happens that you need to bound all the remaining 4 other terms. But so that's why at this point is where we could only bound these 4 other terms for the Bencke modifier. The point is for an arbitrary function, we do not know how to bound it, but for the Bencke modifier, that's where the hard work comes in. So what we show is we can bound all these 7 terms by poly log k times the matrix norms of qg and p and r. I'm not explicit about them, but they're just some matrices that that work. But again, like prior works, all that they do is they just use the Benkos modifier for just one purpose. It approximates the AND function and it has a nice dependence in the norm. But we really have to explicitly dig out the Benkos modifier, and we require several more properties than what prior works require. So we have a complete understanding of Benkos modifier right now. And that's what we had to do to bound all these 7 terms in the previous slide. And what remains to be done is we have the nice polylog K dependence, but we have these matrix norms now. And to upper bound this matrix norm, we use something called the matrix Rosenthal identity. And it's a version of Chernoff. But Chernoff only allows you to upper bound the maximum eigenvalue, but we need to bound the Schatten norms as well. And it gives good concentration for the Schatten norms of summation xi ai. And I think there might be folklore results of also bounding Schatten norms, but one nice thing that we require about this Rosenthal identity is you can kind of de-randomize it. Well, not de-randomize it, it also works for p-wise uniform distributions. So it was so nice that we can bound this, and also for our PRG construction later, we require everything to work for p-wise uniform distributions. So it so happens that this all works. Right, and putting everything together, we upper bounded this quantity by polylog K times the matrix norms of this, which we further upper bounded using a matrix Rosenthal identity, and we get tau times polylog K. Good. So this is our main invariance principle. And in one slide, maybe maybe 5 minutes, I will try to tell you how to go from the invariance principle to actually fooling a spectrahedron.
So Srini, which properties do you use in this proof? Like you make some assumptions on your spectrahedron at the beginning, right?
Oh, good, good.
And also in this hashing step that you mentioned, is it deterministic or is it a randomized hashing? I didn't quite follow that.
You can make it deterministic. So we use the randomized hashing, but you can make it deterministic. So good. That's a good question. So for the invariance principle, you can make it deterministic, but I think when you're constructing the PRG, it requires a randomized hashing.
Okay, thanks.
And good. So the point is we don't require regularity at all in this step. So let's just say you would like to do a subsequent work on fooling just positive spectrahedron. You don't need regular. This invariance principle is the first step. And then you would like to prove something else. We use regularity in the next part, which I'm going to come to. But here, everything works by only assuming positivity. That's it. Good. So let's talk about.
Will they use like positivity as opposed to just like being a symmetric matrix?
Maybe when I finish this talk, I'll recall.
Yeah, sure.
That's a good question. So let me just tell you anti-concentration. So far so this is a spectrahedron, recall. So x is plus minus 1 to the n, and all these ai's and b's are positive. And so far we have established this, that when I apply the Benkos modifier to the eigenvalues of these matrices close to x and close to g, these things are close. And as I said, this Benkos, what's nice is, I've not shown you this, but actually what's inside this square brackets here is actually close to this indicator function. And end of the day, we would like to fool a spectrahedron, that is the indicator functions, and not the modifier. So we need to go from modifier distance to CDF distance. Right, so we care about this quantity. We care about proving 6 and not 5. But we know that, as I said, same as Harsha Clemens Meka, to go from 5 to 6, they just require to show that the Gaussian mass sitting in the boundary of a polytope is small. But again, spectrahedron is so poorly understood, we don't know how to prove such a statement. Instead, we prove the following. So first, let me tell you what the intuition between this approximation squiggly sign is. What it says is the following. If the eigenvalues sit in a very tiny region, so let's just say, look at the eigenvalues of this matrix summation xi ai minus b. If it's all very close to 0, then this approximation is very poor. This Benkos modifier doesn't do a good job in approximating this indicator function. But if the eigenvalues are very much in the interior, like in the polytope reference, then this approximation is good. So now one thing that's left to do is what we show, that the probability of an eigenvalues of summation xi ai or summation gi ai sitting very close to being very close to 0 is actually small, and that's what we show. So for uniformly random x, the largest eigenvalue of summation xi ai minus b sitting in the region very close to 0 happens with very tiny probability.
So that's a Littlewood author type of anti-concentration. Okay.
Exactly. Good. So that's what, here is where we are using regularity. Crucially, we require to show that summation. So we require all these matrices cannot be too small. We require them to be slightly larger, or at least identity. For example, AI, all these AI should be at least identity. And what we show is like the largest eigenvalue of summation x time AI minus p sitting in this tiny interval, think of tau as a tiny interval, is at most order tau. Right. So prior to our work, this was proven by Littlewood and Offord for just pure half spaces. Erdax improved the parameters of Littlewood Offord in 45. And then OSD proved a version of Littlewood Offord for polytopes. And we generalized OSD further for spectrahedron, but for regular positive spectrahedron. So for sure, we use positivity here. For sure, we use regularity here. Right. And so this is done. So like 7 implies 8 because this squiggly sign, we can take care of it by saying the probability of this squiggly sign happening itself is so small that might as well just, instead of working with 8, work with 7. And for 7, we can bound the error parameters. And again, I'm not told you how to construct the PRG from this, but you can take it from me that once you have equation 7, constructing a PRG is not too hard. That again, just we invoke this result by Meka Zuckerman from 2009. Good. Now done. Let me just quickly, right. So 7 implies 8 and we are done now. So let me quickly conclude. Right. So this was a spectrahedron and we assume all these things are positive. And the main result is we can delta fold the class of positive with M spectrahedron with seed length log, depending on log n, log k, m, and 1 over delta. Right. And right. So some direct open questions are: can you remove regularity? And the regularity came in only in the anti-concentration step. The invariance principle didn't use regularity. The second thing is, can we remove positivity? Yeah, I don't know how to prove this because you have to even prove like even the invariance principle we don't know how to prove. And the thing is, one reason we have to prove a Littlewood Offord kind of theorem is we do not know how to bound the Gaussian surface area of a spectrahedron. So this is some ongoing work we are doing right now. And for polytopes, the Gaussian surface area is just nice. It's just poly log in k. Even in sitting in Rn, it's independent of n. But what's the GSA of a spectrahedron? We have no idea. And I think this is just a natural math question. And improve the 1 over delta dependence. I think for a single half space, you can make it log 1 over delta. And that's by just a beautiful observation that works for half spaces, does not work for spectrahedron. And can we prove a general invariance principle for arbitrary spectral functions? Like here, we prove an invariance principle only for the Benkes modifier, but can we just prove for arbitrary function, spectral function that has like nice properties here, the first, second, third, fourth norms are nice, can we prove an invariance principle? With that, I thank you for your attention.
Thank you very much, Srinivasan, for the very nice talk. That was on behalf of everyone who couldn't unmute themselves. So I think you had a chance to take a few questions along the way, but if there are any more questions for Srinivasan, now would be a good time to bring them up.
So typically in invariance principles, we can replace not only random bits by Gaussians, but we can also take any 2 pairs of I don't know, random variables with similar moments. Does this type of thing extend like to the one that you're showing?
Yes, it directly extends. So we can establish invariance principle between like 2 random variables with matching first and second moments. Okay. It could even work for third moments, but it's just that then you need to look at Freshet series of the 4th order, and we didn't want to bound that.
Okay, because like it should serve you, right? Like the more matching moments that you have, the better. Right. Like the more times you can do in like the Taylor.
Correct. Yes. Exactly.
Okay. Thanks.
So Harsha Clemens Meka went to the 4th order derivatives because it's like it was easy for them, but for us, like Freshet series of the 3rd order already seem very complicated.
Okay. Makes sense.
So Srini, you haven't said much about the actual PRG construction. So compared with the PRG for regular polytopes, do you use the same kind of tools to implement the PRG?
Yes, it's exactly the same. So all these PRGs by Harsha Clemens Meka and then O'Donnell, Servedio Tan, and then Chattopadhyay et al., and then O'Donnell, Servedio Tan, all of them use the same PRG construction that was used by Meka, Zuckerman in 2009. The only difference in all these 4 works were they incrementally kept removing some assumptions of the other.
Okay.
Yeah.
So you mean like PRG is like the same, but the difference is that proofs become harder and harder.
Correct. To establish the invariance principle so that the error dependence is like poly-log in K. For example, like the survey, for example, like the first work, Harsha, Clemens, Meka, they assume regularity. To remove regularity, somebody had to prove a new invariance principle, but it depended on some other parameter, which again, somebody had to improve and so on. But always once they establish invariance principle, they use the same PRG with slightly different parameters, but the PRG looks exactly the same as what Meka, Zuckerman used in 2009.
But maybe just could you just maybe very broadly, like what does this PRG do? What does it do? Like what it or
slightly, wait, let me see.
Well, maybe it's quite technical, but maybe just some.
I don't think it's to describe the PRG. It's just a mathematical object. It's not super technical as to why it works. That might be technical, because that's what the hard work of Meka, Zuckerman was. But to describe the PRG, it's just a mathematical thing, and I'm not sure whether I can describe it like online right now. Like maybe offline, I could tell you more. Yeah, but in our paper, it's just like a half-page argument, like what the PRG construction is. It's not at all technical to describe what it is.
Thanks, Srinivasan. We have more questions.
Also, Tom, I'm not super sure yet whether our invariance principle uses positivity or not. I think it does, but I'll clarify with you after the talk. As far as I recall, invariance principle requires positivity, anti-concentration requires regularity and positivity. But I will confirm it after the talk.
Okay, cool.
Okay, excellent. So thanks again, Srinivasan, for the very nice talk. So thank you all for joining. So I look forward to seeing you all at the next DIMAP seminar. So